In acknowledgement of his uncommon commitments to the field of material science, Kaku has drawn broad attention for emphasizing the progressive potential of the James Webb Space Telescope, JWST. This telescope has achieved notable revelations, including the identification of 6 enormous galaxies that defy previous scientific knowledge. These galaxies, once thought to be beyond the reach of scientific inquiry, present a unique opportunity to expand our understanding of the universe. While the significance of these discoveries is captivating, they also subtly challenge established theories about the formation and evolution of the universe. It is essential to carefully assess these findings, as they highlight the critical role of scientific progress. Kaku, a key figure in the scientific community, is well known for his expertise in both classical physics and quantum mechanics. His unique background, shaped by both American and Japanese cultures, has made him a vocal advocate for exploring the new frontiers opened by the JWST. He passionately supports the telescope's discoveries, sharing them with the public and demonstrating his enthusiasm for expanding our knowledge of the universe. His willingness to actively engage with these new discoveries, which can no longer be dismissed, reflects his commitment to advancing human understanding. Kaku's distinctive and compelling perspective stands out in his reflections on the JWST revelations, which have reignited his passion for discovery. Throughout his career, he has been known for his openness to unconventional ideas, welcoming concepts that challenge established principles. While he acknowledges that Einstein's theory of relativity and Newton's laws form the foundation of much of modern science, he also recognizes their limitations in fully explaining the complexities of the universe. Kaku suggests that the discoveries made by the JWST could potentially revolutionize cosmology. Despite the fact that many of his colleagues remain hesitant to accept this view, their skepticism has sparked questions and criticism, particularly among supporters of the Big Bang Theory and quantum mechanics. Regardless, Kaku remains steadfast in his belief that the JWST has uncovered 6 massive galaxies dating back to the early universe. Each of these galaxies contains more stars than our Milky Way, despite having formed only a short time after the Big Bang. A group of cosmologists has aptly named these extraordinary galaxies universe breakers, as their discovery challenges our current understanding of the universe. If confirmed, these findings would dramatically reshape our knowledge of the early universe, suggesting that its initial stages were far more dynamic and complex than previously thought. The prevailing theory of the universe's origin suggests that after the Big Bang, the cosmos was chaotic, with the first solid objects taking a significant amount of time to emerge. It was believed that galaxies began forming much later. However, the massive galaxies recently discovered by the JWST are already larger than the Milky Way, with their exceptional brightness indicating that they could have been forming stars at a rapid rate, unlike our galaxy, which forms stars more slowly and sporadically. The exact timeline of the first cosmic structures remains unclear, but it is evident that the universe may have initially consisted of isolated stars or small star clusters that later merged to form larger groups. For a long time, it was assumed that such enormous and advanced galaxies could not have existed so soon after the Big Bang. This raises a fundamental question. Is the universe older than previously believed, or did these massive galaxies form sooner than expected? This idea presents a significant challenge to conventional science, which still struggles to reconcile these discoveries with established models. Certain areas of physics have outright rejected these new findings, questioning the accuracy of age estimates. However, Kaku is aware of these criticisms and has openly expressed his views on the matter. He points out that many outdated theories persist due to the influence of prominent scientists, even though these ideas have already been disproven by recent research. Kaku emphasizes that true progress in science comes from empirical researchers who prioritize developing rigorous and precise theories. He also highlights that humanity's understanding of the universe's origins is still very limited, underscoring the importance of continuous testing, revision, and refinement in the scientific process. The concept of the universe's origins was first proposed in 1927 when scientists observed that the universe was expanding, implying that it began from an infinitely dense point and has been expanding ever since. At the time, the idea of a universe with both a beginning and an end was difficult for many to grasp, and even today, scientists continue to wrestle with fully understanding this concept. Regardless, it is essential to remain open-minded about such possibilities, even when new discoveries seem to challenge long-held scientific consensus. History has shown that scientific knowledge is frequently revised. For example, when Einstein was young, it was widely believed that stars and planets were fixed in space. Today, we know that everything in the universe is in motion. Planets orbit stars, Stars move through galaxies at incredible speeds, and galaxies themselves travel through space, the ultimate fate of which remains uncertain. This realization challenges long-standing beliefs and underscores the need for constant scientific inquiry and adaptation. Today, scientists are compelled to consider inconsistencies and acknowledge that theories remain incomplete until they are thoroughly tested and confirmed through observational data. The Big Bang theory, for example, emerged from observations showing that galaxies were moving apart, with the distance between them increasing relative to their separation from Earth. This theory, known as Hubble's law, was further validated by evidence such as cosmic microwave background radiation and the redshift of distant galaxies. However, it is crucial to remember that, at one point, people believed the Earth was flat and that the Sun revolved around it, beliefs based on the best available evidence at the time. Technological advancements have since revolutionized our understanding of the universe. We are now in a similar position, as new data from the JWST contradicts certain previous assumptions, demonstrating that science is always evolving. Experts must remain open to new discoveries while re-evaluating established theories in light of emerging evidence. The remarkable discoveries from the JWST challenge current understanding and prompt a reassessment of long-standing cosmological models. Scientists rely heavily on redshift measurements to determine the distances and speeds of celestial objects. Redshift refers to the change in the color of light when light sources and observers move relative to one another. For example, when a distant light source, such as a star, moves away from us, its light shifts toward the red end of the spectrum. Conversely, if it moves closer, the light shifts toward the blue end. This phenomenon provides crucial data about the motion and distance of galaxies. It is important to recognize that even minor errors in redshift measurements can have significant consequences. As a result, many traditional assessment methods are now being questioned due to the new findings. The challenges posed by these new findings underscore the necessity of refining existing methodologies. While redshift measurements remain a crucial tool for estimating cosmic distances, the unexpected discoveries made by the JWST suggest that some assumptions in these calculations may require reassessment. If the estimated ages of these massive galaxies are accurate, they could fundamentally reshape our understanding of the timeline of cosmic evolution. Furthermore, the implications extend beyond the mere dating of galaxies. If galaxies of such immense size and complexity existed so soon after the Big Bang, it raises profound questions about the mechanisms that govern cosmic formation. Traditional models suggest that galaxy formation is a gradual process, requiring hundreds of millions of years for structures to evolve into their present forms. However, the JWST's discoveries challenge this notion, hinting at the possibility that early galaxies formed much more rapidly than previously thought. Kaku, in his analyses, points out that such paradigm-shifting discoveries are not uncommon in the history of science. He draws parallels to past revolutionary moments in physics, such as the advent of quantum mechanics, which forced scientists to rethink fundamental concepts about the nature of reality. He argues that a similar transformation may be unfolding in cosmology, where new observational data compel scientists to reconsider long-standing assumptions about the universe's origins and development. Despite skepticism from some quarters, Kaku remains an enthusiastic advocate for embracing these findings. He believes that resisting new evidence simply because it contradicts established theories is a disservice to scientific progress. Instead, he urges the scientific community to approach these discoveries with an open mind and a willingness to adapt theoretical models as necessary. Moreover, Kaku highlights the role of technological advancements in driving scientific revolutions. The JWST, with its unparalleled ability to observe deep space phenomena, is providing insights that were previously unattainable. Just as the Hubble Space Telescope transformed our understanding of the cosmos in the late 20th century, the JWST is now pushing the boundaries of knowledge even further. One of the most intriguing aspects of the JWST's discoveries is the potential re-evaluation of dark matter and dark energy. These mysterious components, which make up the vast majority of the universe's mass-energy content, remain largely theoretical, inferred from gravitational effects rather than direct observation. If the timeline of galaxy formation needs to be adjusted, it could have significant consequences for our understanding of these elusive cosmic forces. Additionally, the discovery of massive early galaxies raises the possibility that our models of star formation and stellar evolution require modification. The fact that these galaxies contain more stars than the Milky Way suggests that early star formation may have been far more efficient than current models predict. Scientists may need to explore alternative explanations for how such vast amounts of matter coalesced so quickly into structured galaxies. In light of these revelations, Kaku emphasizes the importance of continuous inquiry and adaptability in scientific thought. He reiterates that true scientific progress comes not from rigid adherence to existing theories but from the willingness to challenge assumptions and incorporate new evidence. The JWST's findings, he argues, should serve as a catalyst for further research, encouraging both theoretical physicists and observational astronomers to refine their models in response to this groundbreaking data. While the full implications of the JWST's discoveries are still being analyzed, one thing is certain: they have opened new doors in our quest to understand the cosmos. Whether they ultimately confirm or redefine our existing theories, these findings represent a pivotal moment in the ongoing exploration of the universe. As Kaku and other scientists continue to debate their significance, one fundamental truth remains: science is a dynamic, evolving discipline, always subject to refinement as new information emerges. With each new breakthrough, humanity takes another step closer to unraveling the deepest mysteries of the cosmos. The JWST, much like the scientific pioneers who came before it, is reshaping our perception of reality and challenging us to expand the limits of human knowledge. Revelations made by the JWST, the new discoveries, constrain researchers to analyze whether these outcomes could be attributed to mistakes in redshift estimations or, alternatively, if some specialists are simply ignoring the ongoing data. This issue requires intensive examination and a detailed review of both the data and the approaches used. Such continuous assessment reflects the growing acknowledgement within the academic community that persistent inquiry is crucial to advancing our understanding of the universe. Thank you for watching this video. We encourage you to share your thoughts and feedback in the comments section below. If you enjoyed the content, please like, share, and subscribe to stay updated on future videos. Your viewership is greatly appreciated, and we look forward to seeing you again soon. This call to action urges viewers to engage with the content, fostering a community of curious minds eager to explore and understand the latest scientific developments. The ongoing investigation of our universe, with its vast distances and intricate structures, continues to astonish and challenge scientists worldwide. From early cosmological theories to the latest breakthroughs enabled by cutting-edge technology, each new discovery reshapes our understanding and pushes the boundaries of human knowledge. One of the core questions in cosmology concerns the origins and evolution of galaxies, massive collections of stars, gas, dust, and dark matter bound together by gravity. Understanding how galaxies form and grow is critical to unlocking the mysteries of the universe and testing established scientific theories. For instance, the Big Bang Theory, proposed nearly a century ago, suggests that the universe began as an incredibly dense point and has been expanding ever since. This idea emerged from observations of the expanding universe and the cosmic microwave background radiation, the residual energy and light from the early universe. However, recent discoveries, particularly those made by the JWST, cast doubt on certain aspects of the Big Bang Theory. With its unparalleled sensitivity, the JWST has identified galaxies that appear far larger and more developed than expected for their age. One such revelation includes 6 massive galaxies that formed between 200 and 700 million years after the Big Bang, an exceptionally brief period in the universe's 13.8 billion-year history. These galaxies, referred to as universe breakers by the research team, challenge conventional theories since they are already so large and luminous at such an early stage in the universe's evolution. The discovery of these galaxies raises intriguing questions about the rapid development of the early universe and challenges existing models of galaxy formation. Traditional theories suggest that galaxies form gradually over billions of years through the merging of smaller systems and the accumulation of gas and stars. The presence of these massive galaxies so soon after the Big Bang suggests a more complex and potentially faster process of galaxy formation than previously believed. Additionally, this discovery highlights the critical role that technological advancements play in transforming our understanding of the universe. The JWST's ability to peer deeper into space and capture faint light from distant galaxies has provided cosmologists with significant new insights into the early stages of galaxy formation. These discoveries have broad implications for cosmology, prompting scientists to reconsider and refine existing models to better explain the complexity and diversity of galaxies observed across vast time scales. These findings emphasize the dynamic nature of scientific knowledge, where new discoveries can spark breakthroughs and open new avenues for research. As scientists continue to analyze data from the JWST and other observatories, the study of galaxy formation remains an evolving field. Each new discovery brings us closer to understanding the fundamental processes that shaped the universe as we know it today. As our understanding of cosmic evolution advances, we are uncovering deeper insights into the processes that shape the universe. The study of the early universe is no longer confined to theoretical models or distant projections. It has become a vibrant research field driven by cutting-edge technology. The James Webb Space Telescope, with its unmatched ability to capture data from the farthest reaches of space, is enabling scientists to revisit long-standing theories and explore new areas of inquiry. The newly discovered galaxies, named universe breakers, challenge our understanding of how galaxies formed and how quickly they may have evolved after the Big Bang. These enormous galaxies, larger, more developed, and brighter than previously imagined at such an early stage in the universe, force researchers to reconsider the mechanisms behind galaxy formation and the speed at which these processes may have occurred in the universe's infancy. The implications of these findings extend far beyond cosmology, with the potential to reshape our understanding of the universe's development as a whole. The debate surrounding these discoveries highlights the inherent uncertainty within scientific exploration. Despite the groundbreaking nature of the JWST's findings, many questions remain unanswered. Science must grapple with the possibility that traditional models of galaxy formation and evolution may need to be completely revised. The new data compels us to confront uncomfortable questions about the timeline of the universe's development and whether our past assumptions about cosmic evolution were based on incomplete or flawed models. As we move forward, it is essential to recognize that science is an ever-evolving field, always open to new ideas and possibilities. The JWST's discoveries serve as a reminder that the academic community must remain flexible, willing to challenge long-held beliefs, and ready to adapt to new evidence. Scientific progress is driven by the willingness to revise outdated theories in response to new data. The discoveries made by the JWST illustrate how a single breakthrough can prompt a re-evaluation of the fundamental principles of our understanding. One of the most exciting aspects of the JWST's revelations is the potential for future breakthroughs in our understanding of the very structure of the universe. The telescope's ability to peer deeper into space and capture light from galaxies billions of light-years away has opened up new opportunities to study the universe's earliest moments more precisely than ever before. The data obtained from this research will help scientists refine their models of galaxy formation, explore the role of dark matter and dark energy in shaping the universe, and gain deeper insights into the forces that govern cosmic evolution. At the same time, these discoveries underscore the necessity of collaboration between scientists across various fields. Cosmologists, astrophysicists, and researchers from diverse disciplines must work together to interpret the data provided by the JWST and ensure that these discoveries are integrated into our broader understanding of the universe. The complexity of the cosmos demands a multidisciplinary approach, and the JWST's revelations are a prime example of how scientific collaboration can lead to groundbreaking advancements in our comprehension of the universe. As scientists continue to explore data from the JWST, they are also refining the tools and techniques used to measure and interpret cosmic phenomena. The precision required to study galaxies that formed billions of years ago is immense, and each new discovery drives researchers to improve their methods and update their models. This continuous process of refinement ensures that science remains a rigorous and self-correcting field, where new discoveries lead to the enhancement of our overall understanding. As we continue to explore the universe, the discovery of these massive galaxies will undoubtedly lead to new questions and hypotheses that will guide future research. Will the discovery of these universe breakers change the way we think about galaxy formation, or even the very structure of the universe itself? Only time will tell. However, one thing is certain. The discoveries made by the JWST have reignited our curiosity and opened new frontiers in the exploration of the cosmos. The JWST's groundbreaking discoveries have set the stage for a new era in cosmology, one in which previous assumptions about the universe's formation and evolution are being re-examined. As researchers work to interpret these findings, they must also consider how future observations and technological advancements might further refine our understanding. The role of dark matter and dark energy. One of the most pressing questions raised by the JWST's discoveries is the role of dark matter and dark energy in the early universe. Dark matter, an invisible substance that makes up approximately 27% of the universe, is believed to have played a crucial role in galaxy formation by providing the gravitational scaffolding for matter to coalesce. However, the presence of massive galaxies so early in cosmic history suggests that our understanding of how dark matter influenced these processes may be incomplete. Similarly, dark energy, the mysterious force driving the accelerated expansion of the universe, remains poorly understood. If galaxies formed and evolved at a faster rate than previously believed, it could have implications for how dark energy shaped the large-scale structure of the universe over billions of years. Future observations with the JWST and other telescopes, such as the upcoming Nancy Grace Roman Space Telescope, may provide further insights into these cosmic mysteries. Re-evaluating cosmic timelines. The discovery of highly developed galaxies at such an early stage in the universe's history raises fundamental questions about the timeline of cosmic evolution. If these galaxies formed much faster than expected, it could indicate that the processes driving star formation, black hole growth, and galaxy mergers were more efficient or occurred under different conditions than current models predict. Astrophysicists are now considering alternative explanations, including the possibility that the early universe had different physical properties or that our models of star formation need revision. Additionally, some researchers are investigating whether errors in redshift measurements, used to determine the age and distance of galaxies, could be influencing these conclusions. Implications for the Big Bang Theory. While the Big Bang Theory remains the leading explanation for the origin of the universe, the JWST's discoveries challenge specific aspects of how the first galaxies formed and evolved. Some scientists propose that modifications to existing models, such as incorporating previously overlooked physical processes, may help reconcile these findings with the standard cosmological framework. Others suggest that entirely new theories could emerge as more data is analyzed. For instance, some alternative cosmological models suggest that the universe may have undergone rapid periods of star formation or that exotic forms of matter and energy influenced early galaxy growth. Although these ideas remain speculative, the JWST's ability to gather unprecedentedly detailed observations provides a powerful tool for testing competing theories. Future research and technological advances. As the scientific community processes the implications of these discoveries, future missions will be essential in building upon the JWST's findings. Upcoming telescopes, such as the European Space Agency's Euclid mission and the Vera C. Rubin Observatory, will complement the JWST by mapping the large-scale structure of the universe and studying dark matter's influence on galaxy formation. Moreover, continued advancements in artificial intelligence and data analysis will allow researchers to sift through the vast amounts of data collected by these observatories more efficiently. Machine learning algorithms are already being used to classify galaxies, identify patterns in cosmic structures, and refine models of star formation. The evolving nature of science. The revelations made by the JWST serve as a reminder that science is an ever-evolving field. With each new observation, our understanding of the cosmos deepens, leading to fresh questions and avenues for exploration. The ability to challenge established theories and adapt to new evidence is a hallmark of scientific progress. While the universe breakers challenge conventional models of galaxy formation, they also open the door to groundbreaking discoveries that could reshape our fundamental knowledge of the universe. Whether these findings lead to refinements in existing theories or entirely new paradigms, one thing is certain: the exploration of the cosmos is far from over. As humanity continues to push the boundaries of knowledge, the JWST stands as a testament to our relentless curiosity and determination to uncover the secrets of the universe. The next decade promises to be an exciting time for cosmology, with new telescopes, technologies, and theories poised to revolutionize our understanding of the cosmos.